Alright, so in this video we're going to be solving systems of linear equations by graphing. I believe this is on page 15 of your packet, so if you can flip there, we're going to be taking some notes. So, to solve a system of linear equations by graphing, we're going to graph the lines of both equations on the same coordinate plane. The solution to the system of equations is the point where your two lines meet. So for instance, when we did the problem with the peaches and the apples, when we graphed them, the two lines intersected at 12, 8, which told us that we needed 12 pounds of peaches and 8 pounds of apples to fulfill both of our requirements of 20 pounds of fruit and to spend a total of $28. So to graph linear equations that are given in slope-intercept form, which is the y equals mx plus b form of an equation, we are going to plot the y-intercept first, and then move from there using our slope, which we also call our rate of change, to find the other points on the line. To graph linear equations given in standard form, we're going to rewrite the equations in slope-intercept form and graph it from that form. So that's why we've been practicing that so far in this unit. So we always need to make sure that our equations are in slope-intercept form before we start actually graphing them. So we can see here both of them say y equals, and so we can tell that they're in slope-intercept form. So for this one, I'm going to plot my y-intercept of 5 first, and then use my slope, which is -2, to go down 2 and over 1. And with these types of problems, I want to try to fill in as many points as possible on the graph. And so my line ends up looking, oops, that's a little too low, like this. And I also want to go up 2 and backwards 1, just to really fill up the entire graph. So that's my first line. My second equation, that's also in slope-intercept form, has a y-intercept at -4 and a slope of 1. So I'm going to go up 1 over 1, filling up the graph, and connect my points with a line. And again, the solution is where the two lines cross. So the two lines cross at the point 3, -1. And so we can actually check to make sure that this is the correct equation by taking and plugging in the point 3, -1 for the x-coordinate and for the y-coordinate. So if I take my first equation and do that, I would get for y, -1 equals -2 times 3 plus 5. So I'm checking to make sure that that is correct. So is -1 equal to -6 plus 5? Yes, it is, because -6 plus 5 is -1. So the first equation works out. I also can check the second equation by plugging in -1 for y and 3 for x to get -1 equals -1. So since both equations were true when I plugged in the point 3, -1, I know that I had the correct solution. So the next one, both equations are not in slope-intercept form. They're actually in standard form. So I need to take and rewrite them in order to actually be able to graph them. So 2x minus 3y equals 6. I need to get it to say y equals. So the first step is always to move the term with x to the other side. That gives me -3y equals -2x plus 6. Now to get y by itself, I'm going to divide the entire equation by -3, the coefficient of y. That cancels out -3, leaving me with just y equals, I always want to leave my answers as fractions. And so this as a fraction, it's not easily divisible, so I'm going to leave it as 2/3 because the two negatives, a negative divided by a negative, cancel to make a positive. So it's 2/3 x. Positive 6 divided by negative 3 is negative 2. And now my equation's in slope-intercept form. So my y-intercept is negative 2. My slope is 2/3. So I'm going to go up 2 and over 3. And again, I'm going to plot as many points as possible until I fill up my graph. I can also go down 2 and back 3 to fill up points in this direction. All right, so the next equation is also not in slope-intercept form. So I'm going to take 4x plus y equals negative 2 and get it to say just y equals. So again, I move the term with x first. So to move positive 4x, I subtract 4x, leaving me with y equals negative 4x minus 2. So that's already got y by itself, so I'm ready to graph it. My y-intercept is negative 2. My slope is negative 4, which is really negative 4 over 1, telling me to go down 4 and over 1. I can also go up 4 and back 1, but I can already see my solution where the 2 points cross, or the 2 lines cross, is at 0, negative 2. So that's my final answer. Solutions to a system should always be written as a point. So it's always going to be a coordinate x comma y. Alright, so for the next example, again, I always check to make sure that the equation's in slope-intercept form. Y equals 2x minus 6, that is in slope-intercept form. So I'm going to plot the y-intercept, which is negative 6, and I'm going to go up 2 over 1, since my slope is 2. Up 2 over 1, up 2 over 1, following the pattern all the way up through the graph. The second equation, 3x minus 3y equals 6, is not in slope-intercept form, so I need to rewrite it so that it says y equals. So I first move the term with the x in it. So I move positive 3x by subtracting 3x from both sides, which gives me negative 3y equals negative 3x plus 6. And then I'm going to divide the entire equation by the coefficient of y, which is negative 3, leaving me with positive y equals negative 3 divided by 3 divided by negative 3 is positive 1x, and 6 divided by negative 3 is negative 2. So my y-intercept is negative 2, and my slope is 1, so I'm going to go up 1 over 1 until I find the point where the two lines cross. And so I see the two lines cross at 4, 2, which I just want to mentally check to make sure that's correct. If I plug in 2 for y, I get 2 equals 2 times 4 minus 6. Which is true, because 2 times 4 is 8, 8 minus 6 is 2. So that equation works. And then if I check the second one, 3 times 4 minus 3 times 2, 12 minus 6 does equal 6, so it works in both equations. And you can just check that mentally by doing out the math. Alright, so I don't know about you, but my page does not have any equations when I flip to this page, so even if yours does, I'm just going to have you cross it out. So for the first one, I'm going to have you write in y equals 2x plus 4 and y equals 2x minus 1. So both of these examples are going to be special cases. So let's see what we get when we graph 2x plus 4, whose y-intercept is 4 and slope is 2. So we're going to go up 2 over 1, up 2 over 1. We can also go down 2 and backwards 1. And if I connect those points with a line, that's my first equation. The next equation is 2x minus 1. So my y-intercept is -1, and it has a slope of 2 as well, which this might actually kind of look familiar to you from before when we were solving just regular equations. Anytime the number in front of x was the same and the constant was different, we ended up having no solutions. And if you can see here, these lines never cross, so this system actually has no solutions. And that's because the two lines ended up being parallel, since their slopes were the same, but their y-intercepts were different. So the next example I'm going to have you do is going to be y equals 3x plus 1 and 2y minus 6x equals 2. So the first equation's in slope-intercept form. So my y-intercept is 1, my slope is 3, up 3 over 1. Can also go down 3 and back 1. And so this is my first line. The second equation is not in slope-intercept form, it's in standard form. So I need to move the term with x to the other side first, giving me 2y equals 6x plus 2. And then I'm going to divide by the coefficient of y, which is leaving me with y equals 3x plus 1, which, again, if we think back to before, the coefficients of y are the same, and the constant is the same as well, meaning this is the same exact line. So if I were to go and graph it, the lines line up perfectly, telling me that they always intersect, so there will be infinite solutions for this equation. So in conclusion, if a system of equations has one solution, the graph will intersect at only one point. If it has no solutions, it will never intersect, or the lines will be parallel. And if there's infinite solutions, the two lines will always intersect. Or it's essentially the same exact line.